Hello friends, welcome to my YouTube channel, and today we are going to discuss about process control principles. This is one of the useful presentation to uh, establish the basic knowledge about process control, and it is useful for instruments engineers as well as process engineers to understand the basic control logics or control loops inside the plants, and which are quite also shown on the PNIDs. So let's start our journey of process control principles. Before that, do like and subscribe my channel. This gives us lots of encouragement to prepare new videos. And trust me, making videos for the channel is not very easy, considering my busy schedule. I take some time off during my lunch time or after office times to prepare videos. So do like and subscribe my channel. Um, so the process control definition is what it is. Process control is an engineering mechanism that uses continuous monitoring of an industrial process operation variable, that is pressure level, temperature, flow, chemical content. Mostly pressure level, temperature, flow are quite common ones, and and algorithms, and then use this information to adjust variable to reach product output specification and objective. So that's the definition of process control. Uh, so every control loop in every plant resembles that's shown in the figure 1. The sensor and the transmitter perform a measurement of the control variable and produce an output signal referred to as a process variable. Okay, and you can see this process variable, sensors and process variable. Sorry, it is process variable sitting here. The controller produces an output signal to initiate a corrective action on the manipulated variable to bring the control variable closer to the desired value, which is the set point. So you can see the evaluation set point is given to the controller, and accordingly it is adjusting to give us the optimal value actually. So this is the control loop diagram. Then you can see this is the process control loop response diagram, and you can see there's a error detected, and then controller mode, and there's a output controller output, which adjusts the errors, minimizes the error, so that your measured value is close to the set point. Um, so we can say that the controller error detector performs a mathematical comparison between the measured signal and the set point. So if there is a difference and error is produced, so if there is difference, the error is produced, and simply stated, the operation of the error detector looks like this. The amount of error and the controller mode block will determine the value of the controller output. The controller mode block also determines whether the output signal increases or decreases with the amount of error. So error is basically process variable minus the set point. So this is quite uh, like can say the basic diagram of how the control loop response works. Again, you can see it is. I'll just zoom in a diagram. Actually, here you can see uh, similar diagram like the previous one, but here are some description, like because every process responds differently. The control mode block determines how much and how quickly corrective action is applied. This controller is referred to as proportional, intentional, and derivative controller. It is called PID controllers, which is very common in the process plants. PID, we mostly go with the PID controllers, and it can do so either slowly or very quickly. An example of quick change would be the change in the flow loop due to shutdown of one or two pumps in the process. Example of slow change would be change in temperature due to failure of heater in the temperature control loop. In this example, the control response would be different. So some are quick, some are slow responses. But idea is that you quickly uh, uh, contain the errors or the set point differences, and and quick response should be there to understand how quickly the loops can, if it is shut down, then you have to quickly shut down the system, and or if there's a control, then opening and closing of the control valves are determined accordingly. Okay, so so another example is that another problem that the controller needs to deal with is a lag time. For example, it may take some time before a temperature sensor responds to a temperature change, which means that temperature signal may not accurately represent the temperature of the process. As you can appreciate, the controller mode plays a very critical role in the process control loop. So hope this is clear. Like controller modes as a so controller modes play a very critical role in the process control. Similarly, local and remote loop is there. Um, because of their non-critical nature, most industrial plants have control loops that do not require the displaying of a set point access of their control variable in the centralized control room. In most application, a field-mounted pneumatic controller takes care of this type of local pressure level and temperature control loops. The controller will either connect directly to the transmitter, or it may have its own measurement element, which eliminates the need for a transmitter. Okay, so this part is clear. Uh, these controller may be panel mounted or may be attached directly to a control valve. The typical field mounted pneumatic controller are shown in figure 3. So we'll see this figure, what figure says. So you can see there's a local and a remote loop. Under this one we have a pneumatic controller, process variable output, and output is connected to the control valves. Hope this is clear. Then there is a control loop. Instrumentation action can be direct or reverse actually. So whether you want to fail close, fail open, these things come into picture. So input direct action, output input reverse action, output. So you can see the reverse actions are there actually. So you can see this is going up, this is going down. If this is going down, this is going up. You can see that's a reverse action. Here if you see it is going up, it is also going up, going down actually. So and instrument or device is directly acting if its output changes in a positive direction as a result of positive change as its input, or vice versa. So that's a direct acting. The instrument or device is reverse acting if its output in a negative direction as a result of positive change in the uh, at its input, or vice versa. Okay, and what is this control loop for direct and reverse action? This is a good time to mention that a feature on every controller allows it to be either a direct or reverse acting device. An electric controller action is switch selected on the controller. To change the action on the pneumatic controller, the measurement signal PV and the set point are physically swapped to make it a reverse or uh, or or direct acting. And in computer controller, action is determined by software program changes. So this can be done by the help of the technician who is doing the reverse or a direct or reverse acting control loops. So you can see this is a direct or indirect action on the multiple instrumentation, where direct in the first ones, reverse, and reverse action. So they are uh, directing acting, direct acting, where we can see there multiple instruments are being changed. So instruments connected together in series will produce an overall action of direct or reverse, depending on the action of the individual instruments and the number of instruments connected together. So this is all shown in the figure 5, and it is important to understand that in order for the control loop to operate properly, the overall action of the entire loop must be reverse. If the overall action is direct, the loop will not be able to maintain a controlled variable at set point. So What does this mean exactly? So basically, you can see that it is saying that overall action of the entire loop must be reverse. Okay, if the overall action is direct, the loop will not able to maintain a controlled variable at the set point. So you can see here in the direct action and direct reverse action, and this is reverse input from output. Okay, so you can see how these are acting to give a final output. Similarly, how this is acting to give a final output in a way that it is a reverse thing. Right? See, it is like it's going down, it's going up, going down, going up. So this is the example on a multiple instrumentation reverse or the direct acting actions. Then similarly, in this same direct and reverse action, there's a fail-safe operations. It is critical in the process control that the failure of instruments or device in the loop will not leave the control variable in an unsafe condition, resulting in equipment damage or human injury. For example, if valve at the outlet tank fails due to the loss of power, it must remain in an open position to prevent tank from overflowing. Okay, this condition is said to be a fail-safe position. So that's a sales safe position. As mentioned previously, in order for the control loop to operate properly, overall action must be reverse. The action of individual instrument in the control loop is established to ensure fail-safe condition. So action on the individual instrument are in a control loop, it is stabilized to ensure a fail-safe condition. So basically, somehow like this means that we have to act in such a position that overall response uh, uh, is such that that the ultimate response is a fail-safe position actually. Okay, and what are the signal transmission strength in the industrial? So the industrial instrumentation standard terms, unit of formula modules. There are a number of industry recognized standard signal used to represent variable in the control loop. Just for review, most common used standard signals are 4 to 20 milliamperes, amps, 1 to 5 volts, 20 to 100 kPa, or 3 to 15 psi. And with the development of DCS and SCADA, which is called supervisory control and data acquisition, another module in the a number of digital signal transmitter protocol have been established. As example, communication from the control loop to field instrument, maybe via the Ethernet network. Okay, discussion of these transfer method are beyond the scope of model. This to show that the standard voltage, current, and pneumatic signal will be around uh, for uh, for a long time to come actually. So seeing the voltage like 1.5 and the pressure 3 to 15 actually. Two-wire transmission loop. What this means like this is called sensor transducer, two-wire transmitter, and 4 to 20 milliamps current, DC power supply to 1 to 5 volt to the controller. So I would say that most measurement loops are two-wire system, and as you can see, figure 6 illustrate a typical example. And this system, a two-wire transmitter is powered by the external power supply. Okay, so which is connected in series with the transmitter. The current signals line are also the power delivery lines. The receiver may be a controller, a chart recorder, or any other instruments. Receivers may accept current and a voltage signal or both. If the receiver is a voltage type, a resistor is placed across it. Its input terminal as shown in figure 6. The resistor will convert the current to voltage. And again, referring back to the figure 6, one of the most common instrument in the control loop is transmitter, which is this one. Its job to translate the signal from sensor input of the signal transmitter standards that we discussed earlier. Okay, so the transmitter are connected directly to the sensors such as thermocouple, RTDs, local cells, and a strain gauge etc., or may be connected across an orifice plate. The transmitter are connected directly to the sensors. Okay, because you can see the sensors and the transmitter, and therefore it is usually located in the field. An example of field mounted transmitter is shown in figure 7. We'll come to figure 7, which is this one. You can see this is the transmitter. Actually, you can see the flow transmitter, and this is the orifice plates. These are the examples. Okay, and also shown in the picture of differential pressure transmitter connected across the orifice plates in order to measure the flow rate. You can see these are the things, and this is the transmitter. Okay, now this slide talks about control elements and final actuator. Final control operation involve the steps necessary to convert the controller output signal into required action to the on the process itself. So if you refer to figure 2, which was this much, this was the final control operation is connected by the final control element or actuator, which is for most plant operation is a control valve. So the control valve is being controlled. Example in the control valve and position model, the control valve has two parts, the control element and the actuator. So the stem which is moving across, it is called the actuators basically, and the control elements are the final elements which is resisting the movement of the fluid. The actuator is usually pneumatically operated diaphragm device that physically operates the valve. Shows the example of two pneumatically operated control valve. So we'll come to see that here. You can see that typically in control valves, these are the diaphragm is sitting between this one and with the pneumatic pressure, the instrument air pressure, these guys are most moving to throttle or open the valve actually. So basically in the this is the calibration scale. You can see that what is the position of the control valve physically in the field actually. Okay, so I think so far it is clear. This slide is talking about air to open or air to close control valve. Control valve are classified by the relation between valve stem position and the flow rate through the valve. These topics were discussed in the valve positioning and training module. So this talks about different training which I gave later. So I just written that. The action of the control valve can be either direct or reverse. If an increasing controller output signal causes an increase in the flow rate through the valve, then the valve is direct acting, or vice versa. So if an increasing controller output signal causes an increase in the flow rate through the valve, then the valve is direct acting. So we have to remember this one, that if it is output is increasing the flow, so it is a direct acting. Or direct acting valve is sometimes referred to air to open or a closed valve. Okay, so if it is direct acting, so air is acting on this one to open the valve, and if the air is not there, so it is failed in the closed position. If an increasing controller output signal causes a decrease in the flow rate through the valve is reverse acting or vice versa, and the reverse acting valve often refers to air to close, fail open, or when the air is not there, it fails open actually. So a control valve is always chosen so that it's fail safe. A control valve action is always chosen so that it's a fail safe. So whether it is reverse or direct acting, and the fail safe positions are always selected in the way the operation requires actually. Action in this content should not be confused with the definition of direct or reverse acting valve taken from valve literature. Refer to the control valve and positioner module. Valve literature defines a direct acting valve in one which closes its ports when the valve stem is moved into the valve body. This type of valve can become either a direct or reverse acting valve in the control loop depending on the type of actuator placed on the valve. So it is saying that okay. is the same valve, same actuator, but due to the operation of the air, it can be either fail safe, fail open or fail close, or direct or reverse acting. So this is just a physical representation that how the valve body looks like, what in the valve stem, air to close pneumatic actuator. You can see the physical, this is the physical one, this is the pictorial representation. So the diagram of a typical control valve using a pneumatic actuator attached to the drive. The stem and hence open and close valve. This is example of AFCCO or a fail open kind of. Yeah, you can see that how this is the instrumentation tube actually. If it is gone, it opens. So it is making to close, air to close. Okay. So a controller has most critical job in the plant, which is to maintain the controlled variable at a desired point. As shown in figure 2, this is the figure 2. A controller has two inputs called set points and PV. PV is process variable, and as discussed previously, the controller produces an output depending on difference between two inputs. So error we saw is PV minus set point. So this is how the control loops looks like. And a standalone controller, the set point values are indicated in two ways. Set point indicator values, final actuator position, actual and action or manual. These are the two ways. The first shown in the red indicates the set point is at 58%. The second shown in the red display indicate the set point at 1.760, which is the actual units of the process. Okay. And for example, it means 1.60 meters. The PV value are also indicated in two ways. The first shown in the green bar graph indicates the PV is at 58%. Okay. The second shown in the green digital display indicates PV at 1.760, which is the actual units of the control variable. The position of the final actuator or perhaps the control valve is in case is shown as 41.4%. This graph, these figures are unclear, and you can see that one as well. Instrument and control loop. So you can see some of the pictures, pneumatic controller, then temperature controller system is there. So figure 11, right? Okay. In B and C. So the picture of local control loops where the pneumatic control is physically mounted on the control valve. You can see this one. I discussed earlier in this model, these control loops do not require a displaying of a set point axis of these control variable in a centralized control. The figure 11C shows a Foxboro 43AP being used as a temperature controller. So this is the trade name. Okay, so this one is direct or reverse action, which means that as discussed earlier, in order for a control loop to operate properly, its overall action must be reverse. Therefore, there must be some method of setting the action of a controller. This adjust is usually a switch labeled as direct or reverse. The controller is direct acting if an increase in the PV causes output to increase. The controller is reverse acting. Increase in the PV causes the output to decrease. And instead of control action is shown in figure 11. So I think this is clear, and you can see increase, decrease, increase, increase, direct, reverse. Similarly, there are more diagrams about direct and inverse acting loops. Okay, so that's you can see the signal conditioning is signal conditioner device which amplify, convert, isolate, or transfer process control signals. You can see the pump FCV, FT is there, IP controls are there, where it is converting into milliamps. For example, in this figure, basically you can see that most controller produces a signal of 4 to 20 milliamps. We can see here, and the output signal is indicated to operate a final actuator. If the final actuator is a pneumatic control valve, then the current signal must be changed to pneumatic signal. Okay, and the signal controller used to perform this conversion is called current to pressure controller, or IP converter. So which is this one actually. More pictures of IP converters you can see here. You can see here. This is how they look like. There are more other like single controller EP, IP, IE, current to voltage converter, and these are other examples. This is on-off controller. On-off control means that controller output is either its maximum or minimum value. So XV only there are only the on-off controllers are there XV, which is on or off, like a switch, like you switch on the fan, switch off the fan actually. So there's no mid value actually. Okay, PID control are very common in the normal process plants, and they are often used because every process responds differently to change. The PID control determines how much and how quickly corrective action is applied. For example, flow rate tends to change very quickly, temperature changes very slowly. Therefore, the control response should be different for each other. So this is under the PID controls. You can see the signals how they are changing on the PID control. PID, it is called proportional, integral, or derivative are all individual adjustment setting on the PID controller. In order for the control loop to work properly, the PID controller must be properly adjusted. Okay, the control loop is said to be tuned when the controller settings and their obtained position are, and a set change in the PV or set point produces a change in the control variable as shown in figure 16. This is figure. You can see this errors and then controller output actually. So the response is considered to be the best possible response to a change. This response is referred to as a quarter wave damping because each wave peak is 1/4 the size of one before it actually. So you can see the change happened here, and then subsequently the change was dampened by the controller action, and you can see it is now a straight line close to the set points. So now we'll see that what is all this proportional only action. The proportional is what the controller compares the PV to the set point. As soon as the PV changes, an error signal is created. Therefore, the final actuator controller needs to do something to bring the PV back to the match set point. The controller provides the signal to move the control valve. Obviously, the amount of controller output determines how much the control valve will move actually. So error detected, then periodic controls are there, PB 50% controller mode, output is 50%. So proportional band produces a controller output which is proportional to the size of the error. In other words, the amount of controller output depends on how much the set point or PB changes. Okay. Okay, this is proportional band defined by the percentage of input change that will produce a complete change of output span, which means that if a controller has a proportional band of 100%, the PV instantly changed by 10%, then the control valve will instantly change position by 10%. So that's the proportional band. Okay. Then it talks about the gain. Some controller uses the term gain instead of proportional band. Sometimes it is much easier to determine the controller output change by referring to the gain. Gain is 1 upon PB. For example, a controller with a band of 100% has a gain of 1. So gain of 1 by 1 PB. PB is proportional band, and so gain is 1. So by using gain, the controller output change can be determined by the controller output change is equal to error times gain. Okay. So if the controller has a proportional band of 50%, the PV instant changes by 10%. The change in the controller value of position will be, so gain is what? So proportional by 50%, so gain is 2 actually. So the controller output changes 20%. You can see how gain is changing the controller output actually. Yes. You can see proportional output changes to the step changes. This means that that the proportional only controller does the job expected of it. So at least until a disturbance or load changes happen, at the beginning the controller error is 0 and the controller variable is stable. The next process disturbance will cause the controller variable to change and controller will act. Unfortunately, the system will recover back to a condition of stability but not with the control variable at the set point. So you can see this is the waveform is there. So this is the disturbance. The gray dashed line is the set point. The red wave is the process variable change due to an upset. Okay. Notice that controller output changes quickly, then settles, but does not force the process variable to equal to the set point. This difference between PV and the set point is referred to as an offset, and the proportional volume controller is not doing anything about it. So you can see it has become normal. Set point is here and there is a gap, so it is called offset actually. So 3 points we have to consider about proportional volume controller. Proportional volume controller is used to process where small difference between set point and process variable is not important. The size of offset which occurs depends on the controller gain or proportional band settings. This is because the gain setting establish how much the measurement signal changes to require or produce a control valve movement of a given size. The higher the gain, the narrower proportional band, the smaller the offset. Unfortunately, the higher the gain, the less stable the process becomes. So we saw the formula of the gain, we saw the formula how it varies, changes the controller output. So P we have seen, now it is integral ones, which is called I of the PID, because a proportional control cannot mm, quite do the job of ensuring that controller variable is at the set point. Additional action is required, and additional action is called integral or the reset action. The PI integral control will produce a change output as long as there is an error. In other words, PI control will produce a changing output as long as the controlled variable is not at the set point. So see, it's trying to change so that the set point is achieved. This means that longer the error is present, the more the controller output signal will be changed and more the control valve will be moved in the appropriate direction. So what happens if the process is very slow to respond, such as temperature control process? The final actuator will eventually be reset to its 0% or 100% position. This is called reset wind up. Assuming that control valve does remain within its operating limit, the drift or the resetting effect will continue in the correct direction until the control valve control error is 0. The reset action provides the needed push to get the process variable back to equal to the set points after the proportional action has stopped acting. So you can see that it tries to bring the variable close to the set point. See, there is an offset over here, and then you can see it is now converged into after this I thing has acted, it is now close to the set point. The PI controller measures the PV, then compares with the set point. If there is a difference, the reset action pushes the PV by changing the control output value. Reset action will stop until PV is equal to SP or SP error is 0 actually. So proportionally tuned PI controller will produce a recovery as shown in this figure actually. Yeah. So I is eliminating the offset which is created by the proportional one. We have to understand this one. So the PI controller reset will repeat its original proportional band response over a set period of time and will continue to do so until error is zero. In other words, the reset time is the time to repeat the change that was due to the proportional action alone. The units of reset time or the integral time are minutes per repeat. Some controllers start this as a repeat per minute actually. So the integral action causes the controller output to change at a rate proportional to the error. The longer the reset time, the slower the controller output changes. The controller with the integral action will eventually reduce the error to zero as the output will continue to change until there is no error. So we have the same slides with different language and trying to understand that offset needs to be zero. So now there's a quick example that PI controller has a PB setting of 100% proportional band and minute repeat setting of 8 minutes. Recall that with the PB of 10%, the gain is 1%. Okay, and a disturbance causes the control variable to change, which causes the PB of signal to change by 20%. What will happen at the controller output? So first of all, the proportional control gain will cause the control output to change by 20% because the gain is 1. Okay. The reset action will cause another 20% to be added to the controller output over the period of 8 minutes. In other words, the original controller output will move the controller valve installed by 20% because of the proportional action, and the integral or the reset action will move the control by additional 20% over the 8 minutes time. So that's the first part, which is the proportional ones, and then integral part actually. So again, we saw here this is the formula for the gain and the band. So 100% the gain is 1, 50% so zero point 0.5, then output is 2. So if the gain is PB is 50, output is 20% for the 10% change in the PV value. Okay, we saw this one again. So hopefully this is clear. And then, so if controller variable has to be returned to the set point after the 8 minutes, the process will start again. The process will start again. This will continue until PV, which is the set point. It turns out that adding reset action, we solved one problem, but many other created another. The output drifting affect the PI controller, causes loop to be unstable. The effect of drifting output can be reduced by reducing the controller proportional gain, which is same as increasing the percentage PB. Okay, unfortunately, the results in a poor recovery to the control variable change. This results in a poor recovery to the control variable changes. So now we will introduce the derivative ones, which is the D part of the PID control. So we add reset or integral action to eliminate the offset, which occur when the proportional only response is used. Reset action will occur as long as there is an error or as long as the process variable does not equal to the set point. In many processes, such as temperature control, there's a lot of lag or delay from the time that a change in the load or some other disturbance takes place on the time that the change in the process variable is sensed by the controller. Okay. To the time the change by, so in many processes such as temperature control, there's a lots of lag or delay uh, from the time that a change in the load or some other disturbance takes place to the time that the change in the process variable is sensed by the controller. So there's a gap in the sensing and then uh, taking the control. So derivative of the rate action looks at the speed at which the process variable is moving away from the set point. The controller's derivative unit looks ahead to see what error it will be in the future and adjust the controller output accordingly. So it is so rate, so derivative of the rate action looks at speed at which the process variable. So now the speed has come. So integral was the offset change, and now the time function, like the rate action, looks into the speed at which the process variable is moving, and accordingly it changes the by predicting what can be the error in the future actually. So that's the role of the derivative action. So a derivative unit will force the output to go to a value instantly that the proportion unit would make it at a certain time in the future based on how quickly the process variable is changing. At rate action has taken place, the controller acts like a PI controller. Some key points about the rate action: if the error is zero, there is no action. If the error is not changing, there is no action. If the error is changing, the output is changed instantly based on the rate of change of the error. So that's the work of the derivative control. Now, how that the rate action works? Rate action looks ahead to see what error will be at a certain period of time based on the rate of change of the error. So, rate of the changes of the error is critical. For example, consider a control variable at that start to change the rate at the rate of 1 degree C per minute. This means that error is changing at 1 degree C per minute. What would PI controller do to fix this error? The controller would attempt to change the position of the final actuator, but because the error is changing so slowly, the response may be too little, too late. That would what would the rate action do to fix this error? The controller will look ahead to see what the error would be at a certain period of time, then adjust its output instantly to the value that would be due to the proportional band. Okay, assume that controller looks ahead in 1 minute. The controller adjusted its output to what the value would be at the 1 minute mark. The derivative action is additive to the controller output signal change. Therefore, control valve movement caused by the proportion and the reset responses. The faster the control error is changing, the larger the output signal change added. The derivative response is proportional to the rate of change of the control error. One way to create the control error is to create it quickly, so is to move the set point suddenly, increasing the controller output uh, due to derivative response. In this case, would be large, possibly enough to the momentary slam the control valve to one it to one its end of its travel. So basically, it is just saying that what is the change in the error with the time. Accordingly, derivative function will act accordingly. Now example where the rate action is used in slurry processes such as temperature loops. The rate action causes the process variable to sterilize more quickly. When controlling processes such as flow that respond quickly, rate action is not required because it will cause the process to swing widely or oscillate. So slow action where derivatives are so proportional plus derivative control in a control at 200 degrees C with the control valve position of 50%. The control range of the process is 50 to 550. The PB is set at 25%. The derivative action is set at 2 minutes. The valve sticks and the control valve temperature begins to rise at 4 degrees C per minute. What new controller output immediately after the change? What is the new controller output immediately after the change? So some calculations we need to calculate what a 4 degree per minute change is in percentage of the control range span. So see this is the range actually. So 4 degree it is changing times 100, 1%. Okay. Therefore, the controller variable is changing at 1% per minute. So we have converted the changes into percentage. Okay. After 2 minutes, the change would be 2%. Just adding actually. The gain is 1 by PV. We saw the PV value of 25%. So 4. Therefore, immediately after the change, the control valve would move uh, to what the P only response would be after 2 minutes, which is gain times 2%, or gain was 4, so 8%. Therefore, the valve would immediately go from 50 to 58%. So we have to add. So hope this is clear. So you can see further PID control, how to say that. So we discussed previously that desired response to a control variable upset is shown here actually. A PID loop is useless without the correct controller setting. If they are incorrectly adjusted, the system might overshoot drastically, leading to an uncontrolled oscillation and places of equipment dislodging themselves from their moorings. Tuning to PID control is an art or a skill which is generally required through the practice. As an operator, you will likely not be called upon to tune a control loop, but you may be required to make some minor PID adjustment to bring the system to the desired conditions. So basically, you can see that how quickly and how proportionally the things are done is based on the combined activity of the PID controls, proportional, integral, and derivative control. So derivative is basically rate of change at which the error is changing. Integral is time thing, and proportional is like how the response is changing based on the gains actually. Okay. So now we'll go quickly to the DCS, decision control system. You can read the definitions over there. What is the DCS is all about? Then it looks like this. Basic DCS controller is there, and they are being looped up into the primary server. And then there is a this is the SCADA system, supervisory control and monitoring station, or these are the sensor actuators. You can see this diagram and learn from this basically. So unit performing the PID functions are placed in the location closer to the sensor. We have to remember that. And transmitters and our final control devices are an actuator. So this figure illustrates the basic TCS, and the remote control station communicate to the digital bus or data highway that connects the individual controller units with operators, computers, console, and displays. And in this approach, control room operators have access to all controllers data such as set points, PV measurement, controller output signal levels, etc. Each of these controller units are computer because they are all connected together on a data highway, and each can be programmed for the central control loop operation actually. So it's just more about DCS. The actual remote control station may be control several loops at one edge connected to the several sensors and actuator. We saw that, and since the introduction of DCS, PLC has become capable of PID control in addition to being able to control simple on-off device. Because these PLCs are now becoming a big part of the data highways, DCS may employ one of the several workstation and can configured at the workstation or by offline personal computer. A server or our application process may be including system for extra computation, data collection, and reporting capability actually. So you can see remote control. We would find that number of input-output modules that interface the field device such as sensor and actuator for the controller module itself. Okay. So now distributed control is one form, another will almost completely replaced traditional centralized control room. New installation plant retrofits have done away with the old style control room structure and was equipped with standalone controller, chart recorders, and the indicators. So now this more advanced, and look at the picture how they look like actually. So again, this picture is still old. Now the new plants are have a much more sophisticated display system. Big screens are there, touch screens I have seen in the DCS when I go to the more modern plants actually, and plus it is quick shifting of the screens as well. I have seen. So what is the PLC? The Programmable Logic Controller (PLC) or a programming controller is an industrial digital computer which has been ruggedized and adapted for the control of manufacturing process such as assembly lines or robotic device or any activity that requires high reliability, ease of programming, and process fault diagnosis. PLCs can range from small modular device, 10 inputs, output in a housing integral with the processor, or large rack modular device with a count of thousands of IOs, in which they often network to the other PLC and SCADA systems. So how they look like is this one. You can see input sensor devices are there, a power supply module, central processing, memory, and these are programming devices, output devices, and yeah. So this is the you see how this is working at processor. So a basic PLC structure is looks like this actually. Yeah. Now, uh, s- so we will do some quick comparison of the of this one. Okay, and we will quickly talk about uh, this SCADA system as well. Or let's do quickly about the comparison actually. So how it looks like, we will do quick comparison as well. And PLC and DCS, like high level programming language and ability for the creating custom language, custom logic created with existing function blocks. DCS and PLC, customized routing usually required. Many algorithm PID of the do not vary among application. Standard libraries are considered nice features. Standard application are expected. So these are some of the PLC and DCS ones. And this is the SCADA system where we're talking about supervisor control and data acquisition. SCADA in the control system acquisition comprises computer, network data communication, and graphic user interface or high level process management, while also comprising of the other peripheral device and logic control. So SCADA architect is this one, and this is the HMIs actually. Yeah. Okay. So HMIs are basically human machine interface where the operators actually sits and changes the inputs and all. So with this, we have come to the end of the our our control loop principle presentation. Hope you enjoyed this video and do like and subscribe my channel. Thanks for watching again.